Hello. Hello everyone. My name is Yuhan Yao. I'm a postdoc at UC Berkeley. Today I want to present a detailed study on the TDE called AT2022 LRI. And my goal is to convey to you how we inferred the existence of subrelativity outflows and very rapid hour timescale mass accretion rate drops during the super-Eddington accretion of this source. So black hole super-Eddington accretion has always been a fascinating subject of black hole research. People have identified quasars with black hole mass more massive than 10 to the 9 solar masses when the universe is nearly 7 million years old. So how did they grow to be such a massive in such a short amount of time? So here the red lines show the growth history assuming constant Eddington limited accretion rate. And the blue regions show the mass ranges for different black hole seed scenarios. So as you can see, for lower mass black hole seeds, the mass accretion rate needs to exceed the Eddington limit for some amount of time. And this process potentially governs the growth of the very first supermassive black holes, the impact on their host galaxies, and the epoch of reionization. But observationally, super-Eddington accretion is not very well characterized because most nearby AGNs are accreting at low accretion rates. For the very rare example where you have super-Eddington accretors, the disk emission peaks in the extreme UV band. So it's rather hard to study the hottest part of the disk where most of the gravitational potential energy is released. And so TDEs in low mass black holes has been proposed to be very good labs to study black hole super-Eddington accretion. We need low mass black holes for two reasons. First, the basic theory predicts that the mass fallback rate is only above the Eddington limit for a very long time when the black hole mass is small. And second, lower mass black holes generally have the inner disk temperature that's hotter, which makes them peaks in the soft X-ray band where we can observe. So among the optically selected TDEs in this flux limited sample, about a third of them are hosted by black holes with a total mass that's less than 10 to the 6 solar masses or so. So there is a good number of events in lower massive black holes. But if you look at their X-ray light curve, very few of them show sustained super-Eddington accretion phase, as Muriel just showed. And there have been lots of theories proposed to explain this lack of observed X-ray emission. One of the theories is the reprocessing picture, where if you look through the optically thin funnel, you can see the exposed accretion disk, which gives you strong X-ray emission. But if you look through other viewing angles, the X-rays are just reprocessed into the UV and optical band via photoionization or diabatic reprocessing. This is recently updated by simulations presented by Thomson 2022, where if you compute the UV and optical black body luminosity to the ratio of the soft X-ray luminosity, you can see that the X-ray is only brighter than the UV and optical when the inclination angle is small. Another very interesting prediction under this black hole super-Eddington accretion picture is the existence of fast and slow outflows. So if you imagine that there are some ionized outflowing materials above a continuum source of disk emission, the outflow will create both absorption and emission features that is at different energies depending on the velocity. The very first evidence of fast outflows in the TDE X-ray spectrum was reported in a 2014 LI, where you see a strong P Cygni profile signature with the absorption minimum that's about 0.7 keV. This can be attributed to oxygen 8, blue shifted by 0.2 C. And more recently, nicer data on this TDE AT2020 KSF showed absorption features that is consistent with oxygen 8, neon 9, and iron 17, blue shifted by 0.14 C. In addition to this absorption modeling approach, an alternative way to think of the picture is that the inner disk, a fraction of the emission can be reflected off the surface of the ionized outflow. And this model was actually developed fairly recently to explain the X-ray spectrum of this 1ES 1927-654 source, which is likely a TDE in a pre-existing AGN. So the model's name is Silver TDE, presented by Masters in 2022. Here to explain this very strong residual that peaks at 1 keV, you need this broadened silver TDE reflection component to be blue shifted by 0.33 C, and this again indicates the existence of very fast outflows. In terms of low velocity outflows, they have been found in as narrow absorption lines in high resolution X-ray grating spectra. For example, we have detections of few hundred kilometers per second slow outflows in Assassin 14Li, as well as this more recent Assassin 20 QC, whose RGI spectrum is shown here. But I do want to highlight that you need the TD X-ray flux to be relatively bright to do this sort of high quality, high SNR X-ray spectral study in order to search for fast or slow outflows. And this brings me to talk about the uniqueness of this particular TDE. AT2020 LRI in its X-ray luminosity alone is above the Eddington luminosity for a very long time. So it shows evidence of sustained super Eddington accretion. Also, we observed very fast hour timescale X-ray variability in the light curve, and the X-ray spectrum is very soft, so there is no on-axis jet. Those two in combination has never been observed in any other TDEs before. And because this nearby event is so bright, we were able to have high cadence and high SNR data using the NICER, XM Newton, and Swift telescopes, totaling more than 1 millisecond of data. But to tell the story from the very beginning, I want to first give a brief summary of its UV and optical properties. So this event was actually first identified by the Atlas Sky Survey. You can see that there is maybe one data point on the rise. Unfortunately, we missed the peak due to sun constraint. The decline was first picked up by Atlas and then by CTF. In October 2022, we classified it as a TDE based on the existence of broad hydrogen and helium emission lines that you commonly also see in other CTF TDEs. The UV and X-ray follow-up observation started about 190 days after the optical peak. If you fit the UV and optical ICD with a black body, you can see that its black body temperature and radius parameters are pretty typical for an optically selected TDE at such late phase. The host galaxy does not have any AGN emission lines, nor does it have any historical X-ray detections, so it's a quiescent host. My collaborator Msun Li at Peking University did a disk bulge decomposition using archival images, showing that it has a pseudobulge and a disk component that is close to be viewed face on. In terms of the black hole mass, there is quite a large uncertainty here, because using different scaling relations, you get different answers. So one thing that I'm sure is that it's definitely on the lower end of the MBH distribution of TDEs. So somewhere between 10 to the 4 and 10 to the 6 solar masses. In the remaining of this talk, I will sometimes adopt a somewhat intermediate value of 2 times 10 to the 5 solar masses. But we should bear in mind that there is this uncertainty in MBH here. Okay, X-ray light curve. So here I'm showing the NICER light curve in blue and the Swift light curve in red. You can see that the TDE has very rapid X-ray flux drops on top of what seems to be a long-term power law decline. At later times, the variability and the drops seem to occur at lower frequencies and the amplitude is smaller. And we did a period search on the light curve, find no evidence for any periodicity. If you zoom in onto the early time, very crazy light curve behavior, and if you zoom in further onto this region, you can see that the flux changes back factor of 2 within 30 minutes and back factor of 8 within just 1 day. The X-ray spectrum is very soft. It can be to zeroth order, fitted with a multicolor disk and a weak power law component to account for the hardtail. So by fitting the time-resolved XRT and NICER observations, we measured the X-ray luminosity, which is shown in black, and in comparison, we're showing the UV and optical black body luminosity in green. And if you do the ratio, you will see that the X-ray is, for most of the time, more than order of magnitude brighter than the UV and optical black body, except maybe during times of the strong X-ray dips. A very crude way to estimate the bolometric luminosity is to just connect the 0.3 keV observed X-ray flux to the SWIFT near UV photometry. And if you integrate below this SED, you get a bolometric light curve that's decaying from 3 times 10 to the 44 to 6 times 10 to the 43 ergs per second, which is always above the Eddington limit, assuming a 2 times 10 to the 5 solar mass black hole. But even if we adopt this high black hole mass estimate of 10 to the 6, the early time bolometric is still above the Eddington limit. So we are pretty sure that this is a super Eddington accreting source. And because of that, we can compare with the Thomson 2022 simulations. In order to get the same ratio, we need the inclination angle to be less than 30 degrees or so. And there's some discussion in the paper saying that this optical black body is maybe a little underestimated. So the actual inclination of 2022 LRI is maybe even smaller. Here shows the evolution of the X-ray spectral parameters. Again, the top shows the luminosity. The second panel shows the ratio between the power law component to the flux of the disk BB component. You can see that there is maybe a slight increase at later time, but this power law flux contribution never exceeds 20%. So it remains pretty weak. The bottom two panels show the inner disk temperature and the apparent inner disk radius. But because we know that inclination is small, so this is a good approximation of the inner disk radius. You can see that the drops in the luminosity is very strongly correlated with the drops in the inner disk temperature, whereas the inner disk radius remains relatively constant at 2 times 10 to the 11 centimeter. And if we assume a 2 times 10 to the 5 solar mass black hole, the gravitational radius is 3 times 10 to the 10. So here the inner disk radius is pretty consistent with being at east core of a non-spinning black hole. But as I said before, the X-ray spectrum is only consistent with the disk BB plus power law to 0th order. Actually, there are spectral features. So here I selected 2 observations show the spectral fit here. You can see that maybe in this observation, there is this residual around 1 keV that can be accounted for if you just add 1 Gaussian line emission. But in this observation and in some others, this residual feature is just so strong such that it's not possible to explain it with just 1 line. You need to consider those physically motivated models, either absorption or emission from some ionized material or reflection of this ionized material. And in both cases, they can fit the observational data. And in both cases, we require some fast outflow with velocities from 0.1 to 0.3 C. And knowing that, we want to further ask, how does the accretion inflow and outflow properties change during times of the strong X-ray dip? So to answer that, we selected 7 observations during 1 X-ray dip and modeled their X-ray spectrum using those 2 physically motivated models. So here is this first model, just to remind you. Here we are considering some ionized outflow, covering the disk, creating some absorption and emission features. For those of you who are familiar with S-spec terms, here is the full model's name. In the very last observation, we also added a power law component to account for the hardtail above 1.5 keV. We jointly fit the spectrum, but allow the disk temperature, radius, and column density of the outflow to change across the different observations while fixing the ionization state and the outflow velocities. The best fit indicates an outflow velocity of 0.11 C for the absorption component that's obscuring the disk, 0.16 C for the emission component integrated along the line of sight, ionization of log 3 equals to 3, and column density that's changing across different observations. So NH is largest when you have the lowest X-ray flux. But I do want to note that even our largest column density of 4 times 10 to the 21 is still small, such that it can only cause a flux decrease of less than 20%. So the change in column density is not the reason why we observe this factor of 7 total flux change. And in order to have this very large amplitude total flux change, we need the disk temperature, we're seeing that the disk temperature is changing very rapidly, and the luminosity is correlated with the change in temperature. So this is the first model. In the second one, we're considering refraction of the accretion disk, accretion of the outflow using this silver TDE model. And the best fit gives us a pretty fast outflow velocity of 0.34 keV, ionization of log psi equals to 2, and a pretty dense gas density of 10 to the 19 per centimeter square. If you look at the what's contributing to the total flux change, you'll see that this comes from both the change in the black body disk component as well as the reflection component. And the disk component change is, again, very much correlated with the change in inner disk temperature. The reflection component comes from both the change of the ionization temperature as well as the normalization. So maybe the amount of surface area that's available to reflect off the disk emission is also changing during the observations. So just to summarize the results of the two models, both of them provide good and statistically comparable fits. And in both cases, we require the existence of subrelativistic outflows. And from our analysis, we think that the very strong, rapid hour timescale X-ray dips are caused by instantaneous drops of the local mass heating rate and the mass accretion rate at the inner disk radius. This is supported by our spectrum modeling, whereas other explanations like Lancerian precession and massive black hole binaries typically predicts a variability timescale that's longer than the observed one. And now the question is, what is the underlying triggering mechanism that's causing this very rapid accretion rate change? By reading the literature, I think a very promising scenario is instabilities in the magnetic field. For example, in magnetically arrested accretion disk, you can have regions with strong B fields creating underdensities in the disk material that erupts outwards. In the simulation by Kurt and Neri in 2023, they performed TDE super-identity mag simulations, seeing that flux eruption events can cause variability on the timescale of 1,000 TG. So TG is just GM over C cubed. For a 2 times 10 to the 5 solar mass black hole, this is 1 second. So this can easily explain our observed variability timescale of less than 1 hour. Okay, so just to briefly summarize our results, we inferred the existence of subrelativistic outflows and sudden mass accretion rate drops in this super-identity accreting TDE. I didn't have time to show the XFM RGS spectrum, but we do not find any evidence for narrow absorption lines in the data, indicating that either the low velocity outflow is non-existent or is too weak to be detected. We think that the inclination angle of this system is very small. We are viewing it close to face on, and the rapid variability is sort of consistent with a mad disk with a non-spinning black hole. And there are still many open questions that I want to discuss with you. Here are a few of them that I listed here. And I'm very interested in your opinions about our analysis and interpretation. Do you think if there's something that we have overlooked in our data? Yeah, so with that, thank you for listening, and I'm happy to take any questions.
All right, thanks for the great talk. Anyone have any burning questions? All right, well, I have one while we are waiting. So is there any periodicity to these dips, or does it just sort of seem to be completely random?
So we did a period search using Lomb-Scargo and multi-harmonic AOV, and both algorithms give no periodicity significant peaks. So I think they are pretty random.
Okay, interesting. We'll go to Vikram.
I've also got a question. Based on your modeling, Yuhan, especially of the reflection or reprocessing in the layer, in an outflow, what do you think it would have looked like at a slightly larger inclination?
So the inclination is modifying the line profile. Yeah. If it's the relativistic effect is very strong.
Yeah.
But some simulations show that in this super Eddington accreting phase, especially if your inclination is small, the symmetry of the profile won't be changed very much. So here we are just convolving the reflection component with some smooth Gaussian component. And we are not including the relativistic line profile in the modeling.
But do you think you'd have seen the fast extra variability from different inclinations?
I think it's easier to be seen from phase on.
Yeah.
So that's another reason why we think it's phase on. Yeah. From other, I think from edge on, it's pretty hard to see because it's just obscured.
Yeah, right.
Yeah, maybe that's one reason why we don't see this in many other TDEs. Yeah. Because you need a specific geometry.
Yeah. Thanks.
All right.
So you said this type of phenomenon is very rare. So how rare do you mean rare? Is it 1% TDE rate? If it is opening angle of 10 degrees, does it 10 degrees solid angle fraction of 4 pi? Does it already explain the rarity?
Maybe, but I haven't do the calculation yet. I think to answer this, you also need high cadence observation for other systems. And
so we don't know whether other ones have such.
I think for a few of them, we do know that they don't exist. But for many of them, we only have a little bit, like 4 or 5 swift snapshots where you can't really tell if there's fast variability here.
I see. So
yeah, I need to better quantify this.
Yeah, you need to maybe quantify. We can talk about this later, but maybe we can quantify how rare they are actually. And yeah. See.
All right, I think you were in line next, and then we'll go over there.
Okay, yeah, very nice talk. I have a question. At the very beginning of your talk, you mentioned that probably we can use this super Eddington accretion to explain the growth of the supermassive black hole. So my question is about the rate, like the TD rate per galaxy for like 10 to the 6 solar mass supermassive black hole is 10 to the minus 4, 10 to the minus 5, something like that. And Eddington accretion rate for the supermassive black hole is 10 to the minus 2 solar mass per year. So my question is this rate sufficient enough to support the mass increase from this super Eddington accretion from TDE? Like the accretion rate, like the TD rate is too low to support the mass, the super Eddington accretion.
Yeah, so we are not saying that TDEs accretion is the reason that the very first supermassive black hole formed. We are just saying that we can use TDE super Eddington accretion to characterize how the super Eddington accretion looks, and maybe that can tell us in those very first supermassive black holes in the universe how fast are their outflows being launched, and how's the kinetic energy, how do they impact their environment.
Yeah, but the TD rate is per galaxy is only 10 to minus 4, 10 to minus 5 per year. And if you want to like keep like this super Eddington accretion constantly, you don't have so many stars in the nuclear star cluster.
Oh, they are only super Eddington for like a few years, 1 year to a few years. So they, sorry, what's yeah, so you think there's not enough stars to feed super Eddington accretion for such a long time?
Yeah, for such a long time, yeah.
I'm not sure. The super Eddington accretion rate is like 10 to the minus 1 solar mass per year.
10 to minus 2 for a 10 to the 6 solar mass.
So for one single TDE, you only need 1 star.
Yeah.
So you only need 1. I don't know what's the problem.
Like if you want to keep a super Eddington accretion for 10 to the 6 solar mass supermassive black hole, you need a disruptor 0.1 star per year, but your TD rate in this galaxy is only 10 to minus 4, 10 to minus 5. So this.
Oh, I think she's not saying this is how you grow the black hole entirely. It's just you can use it to study this phase, and then whatever was feeding the black hole at that rate, you learn something about
anyway,
it.
Yeah, we can discuss later.
Yeah, maybe we can maybe we can discuss more, and let's try to sneak in 1 or 2 more questions before we have to move on.
So you said that the black hole mass is uncertain, so I guess there's a way out of this, but you have modeled this as a thin disk.
Yes.
But then you said that most likely it has been super Eddington the whole time.
Yeah.
So the fact that you probably successfully modeled it as a thin disk, doesn't it maybe suggest that the mass is higher than the optical data would suggest, and that it's not super Eddington? Or if it is super Eddington, then maybe all the residuals from the thin disk model are due to the fact that we don't model super Eddington accretion flows that well, rather than maybe outflows or power laws.
Yeah, I did try this slim disk model. Some of the available models for super Eddington disk in expect, and they also leave strong residuals. So I think the features that you see cannot be totally accounted for if you just change your disk model.
Okay.
Yeah, but I do agree that maybe disk BB is not very appropriate based model here.
I mean, yeah, it's fine. It's what everybody uses because it's nice and fast. But like the fact that you do see a fairly thinnish disk in a soft X-rays, it could be a more direct evidence of a relatively higher black hole mass, so that the accretion flow is not maybe super Eddington. Or do you think that's not?
The super Eddington mainly comes from the luminosity alone. The luminosity is above the Eddington limit. So it doesn't depend on, it's not model dependent.
No, but the black hole mass that you get from the M sigma or M star.
Oh, I get it from galaxy scaling relations.
Yeah. Okay, yeah. Yeah, we can talk later. I think I didn't make my point clear. Sorry, we'll talk later.
Okay.
Go ahead.
My question is likewise kind of technical. How correlated is how you take into account like the higher energy emission, let's say above 1.5 keV, and the features that you see in like your outflow model, basically?
The 1.5 keV part can mostly just be accounted for using a power law. Yeah, so it's mainly the...
Yeah, like the okay, well, yeah, I don't want to take other time, maybe.
Yeah, I think we have time for maybe, if one of you has a quick question, we can do that and we'll swap out the computers.
So yeah, I like the model of the magnetic arrested disk on the previous slide. So yeah, so do you expect like a correlation between the accretion rate and the outflow velocity? And do you think that can be measurable in future TDEs?
Yeah, I think maybe when the mass accretion rate drops, the outflow rate increase, and there might be a correlation. But in order to measure that, you need very high quality data at each point of this variability. And yeah, I think we do have high quality data at certain time, but not at every point. Also, like at the X-ray dips, when it's at the dip, we only have data up to 1 keV because it just gets so faint. So it's a little hard to measure the outflow velocity during the variability. Yeah.
Thank you.
All right, let's thank Yuhan again.